Good afternoon, all. In our lab, I think we have completed total 5 experiment, right? And today we are supposed to start with experiment number 6. Am I right? Hello. Use your mic. Unmute yourself and give me answer instead of typing there. Yeah, I got your yes from that chat, but it is better to say yes, right, without typing it. Okay, so we'll start with that experiment number 6 today. That experiment number 6, if I give you the aim, then it is the verification and implementation of 1-bit and 2-bit digital comparators. So before that we go into the simulation side, we need to know that what exactly this comparator is. And unfortunately today this virtual lab site is also not working, and it's not getting open today. So before we get it open, let me discuss theoretical aspects, that what do you mean by the comparator and how the digital comparators are going to work, and so on, that thing, right? So let us me start discussing that part. Okay, so suppose, let us say I would like to ask you about that. For example, you have been given some decimal numbers like this. So let us say you have been given, okay, these are the two numbers given to you, for example. And suppose you have been asked to compare these two numbers. So how usually we are going to compare it? What the process we are doing actually? Right? It is just by visual inspection we can say that the 756 is the larger number than the 456, right? But how our mind system is going to react on this? That how it will come up with the answer that 756 is going to be larger than 456? Can you just tell me that? And what the method we are following in our mind? Hello? Am I audible to everyone? Please use to give your answer by unmuting yourself, right? Do not type there. Hello? I'm asking you the question. I've given you two numbers there, and I'm asking that how our mind reacts on that two numbers to compare them. What could be the output for that comparison actually?
So, subtracting the larger number from the smaller one.
Okay, that you are going to do in your mind when you are going to compare the two numbers. Okay, simply having given one answer. What about others? Okay, before we get to know about that thing, can you just tell me that when I say word comparator or comparing something, particularly the numbers, what exactly could be the output of that task of comparison? Yes, anybody of you? I'm asking you a very simple question. Don't get in much detailed way that what could be the answer of this question. I'm just asking you a very simple thing. That when you are doing the comparison of two things or two numbers, what could be your answer? What could be your output? Yes, no one is giving answer about this question. This question is going to be difficult for you. Hello, am I making my question clear to everyone? That what exactly I'm asking to you? Hello. Hello everyone, what are you thinking for? I just asked you a very simple question about the comparison. And when you are doing the comparison, what could be your output? What could be your answer? Why you need to think so much on that? Are you following what I'm asking to you all? Nehil, can you hear my question? Hello. Shubham, can you hear me? Just please unmute yourself and give me answer. Not type there. I'm asking this thing many times to all of you. Hello. Emalin, can you hear me? Can you just let me know what exactly you are knowing about that thing? Whether it is right or wrong, don't worry. It's not I'm asking you for an exam, right? But if you say wrong answer, it's not going to cut your marks. Just say me whatever you know. When you are doing some comparison of some items or let's say some numbers, what your answer should be, or you can say what your output should be.
Sir, a difference between these two numbers?
Okay, who is saying this? Difference between this number? Yes, is giving the answer. Okay, okay, that is just like Nesagi has said that subtraction. Okay, so two answers I got for this question that you are asking me like the difference of the two numbers that would be the output. Okay, anyone else would like to add something in your mind other than this what these two people have said? Subham, Kevin, Hemali, do you like to say anything about this? And why only five people are here in the live session right now? Why are others? Yes. Can I know the reason that why we play so much less strength here in our lab? Is there any other task given by your class? Like any class test or something else? Yes, Naisagi, can you hear me?
Yes, sir.
Is there like so that you have any other subject exam or something like that today?
No, sir, there is nothing like that.
I am looking here only five or six students.
So it's the same in other labs too.
Oh, no, this is I'm looking here first time, because in our lab session I've seen already more than 10 students every lab, maybe 12, 13, 15 students are there always. But today only I can see here very less students. Anyway, let's we go ahead. So what I was asking you about the comparison. That means whenever you are making comparison between the numbers or let's say two items, what exactly we are doing? We are first looking at that whether the two items are same or not, right? Likewise in numbers also. So very first answer what we could have at the output is whether the two numbers are equal or not, right? So you can say if that two numbers are equal, you say that your answer is 1 for that. If that numbers are not equal, then the answer for that question will be 0 at the output side. So this is the first output you could have at the output side, that whether that two numbers are same or not. Now second thing is that if that two numbers are not equal, then there could be two other options. Either your number A can be less than number B, or number B can be less than number A, isn't it? Or you can say in other word like your number A can be less than number B, or it can be greater than number B, isn't it? So here, if I just talk about these two numbers, what I given to you, that the number 456 and the number 756. If you take one comparator block, or you can say some comparator circuits, so what that circuit will do, let us say this is your comparator. So the task done by this comparator is what? That it will take your two numbers at the input side, that is let us say number A and B, what you can give at the input side, and then after it will give you three outputs. By taking two numbers at the input side, your output will be 3. That is what? It gives you either A equal to B, that is one of the possibility, or your A greater than B, or the third possibility, that is what you can say A less than B. So these three can be at the output side. Right? Now out of these three, at a time any one can exist, right? If your A is greater than B, then your A cannot be equal to B, as well as A cannot be less than B, isn't it? Likewise, you can check for all any of these three, that at the output, at any point of time, you can have only one condition that is true, remaining all are going to be 0. So we can say that the comparator output will be logic 1 for the case which is coming there. That means if your numbers are equal, then A equal to B will be having logic 1 and remaining 2 will be having logic 0. And if A greater than B is there, then you can say the first condition, A greater than B will give you output logic 1 and remaining 2 will be logic 0. Likewise, out of these three output of the comparator circuit, you will have at a time only one at the logic 1 and remaining at the logic 0. Am I making this thing clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So, see, this is what we are exactly doing in the comparison. We are not going to do any kind of subtraction there, because you have not been asked to find out what the difference between them is. And when it is asked you to do the comparison, you will not be looking at that what the difference between them is. You're just going to tell them, or just going to give you the answer like which is the condition going to exist there, whether they are equal or less than or greater than. So that's what the meaning of comparison is, right? Because comparison do not means to give you the answer of subtraction, or do you find the difference out there for that. Okay, so this is what the thing about that. Now, when you come to the binary numbers and you want to do the comparison of binary, before that, let us take this decimal number itself. Suppose you take the same example which I given to you, these two numbers. You consider these two numbers, okay? Let us say this is your number A and this is your number B. So how you will be going to compare these two numbers to give this any one of these answers? Can you just now tell me about this thing now? I given you two numbers A and B, right? We can directly say that your number A is less than number B. That could be the condition at the output side. But how our mind is going to find out this thing? That your answer is A less than B, not A equal to B or A less than A greater than B. Can you just tell me about that thing?
We have to check the number of digits first for both the numbers.
Yeah, very good. And then after?
Then if both are equal digit numbers, that is 3 digit, then we have to check the leftmost digit. So which one is greater?
Okay. Let's say these are both numbers having 3-digit numbers. Okay. So then what we will do?
So we have to check all the digits turn by turn. So if we get any number which is greater than the digit for the next number, then it is greater or it is equal or it's less.
Okay. Okay. Very good. So that's what we can say. It's ones, tens, hundreds, like thousands. If you're getting number of digits increased in that order, you will be having that thing, right? Right now you can see this is the two numbers. In that, what are the position weight of that three numbers, 3 digits? That is, you can say 6 number digit in each of that number will be coming in the position of ones, right? Then the number 5 coming into the position of tens, and number 4 and 7 that's coming into the position of number hundreds. So what we will be doing is we'll be comparing these two numbers by comparing them starting from most significant bit. That is, let us recall here. This is what your MSB, or you can say most significant bit. I can say this is higher significant bit or most significant bit, we can say, and we'll move towards, this is what you can say, least significant bit, LSB. Okay. Exactly what I can say is that number 4, 5, 6, that is what I can say. It will be, you can say, like A2, A1 and A0. These are the three numbers for the number A. Right. Likewise, 7, 5, 6 is for that, you can say B2, B1 and B0. So what normally we are doing is, first of all, we'll be going to compare the numbers A2 and B2. That is what you can say most significant bit, right? Or you can say most significant digit in case of decimal numbers. So when you compare this most significant digit, you will be first coming to know that is they are equal or not. If they are equal, or whatever condition is, suppose this is 7 and 4 in this case, so it is just letting you know that your number B is going to be greater than number A, right? Just by comparing your MSB digits only. Once you come to know from this, it's not necessary to go to compare that number 5 and 6, or you can say number A1 and B1, A0 and B1, right? A0 and B0. Why is that so? Because your higher position bit is itself giving you idea that which number is going to be greater or less than, right? If suppose these are the numbers, let's say like this. Suppose you have been given the number 4, 5, 6 and let us say 4, 8, 5. So these are the two numbers given to you. Then what you can say, when you will be comparing your A2 and B2, in that case you can see they both are 4. That means they both are equal. If your MSB is telling you that if your numbers are equal, you need to more get clear after going to comparing them with the number position tens, and then after you have to go to number position ones. So in that case, you have to go into this kind of position wise comparison, and if you get the answer, then you can skip remaining portion of comparison part, and you can give your answer whether A is equal to B or A less than B or A greater than B. Right, so this is how we are following in case of comparison for the decimal number system that's in our routine life. Am I clear about this thing to all of you?
Yes, sir.
I'm not
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. Okay, so now the actual task which we want to perform today in our experiment, that is to compare the digital numbers. That means we want to perform the digital comparator circuits. So digital circuit, that's what we are using in comparison task. They can start initially from the 1-bit comparison, That means your comparator can be of a number of bits position. Right? For example, you are working with your 64-bit processor in your computer or laptop system. Then that system need to have 64-bit comparators, right? Because in that case, your numbers which is going to come in your processor, they will be of 64-bit size, and that's why you need to have that much size comparator. But if you want to work, or if you are working with the laptop having 32-bit capacity, then in that your computer system will have the comparator size of 32-bit. So that can be used for performing the logical task of comparison. Likewise, you can have a comparator circuit as per your number of bit requirement. That means you can have a comparator as per your number required to be compared, right? So we can start here learning about comparator circuit development or implementation by starting with, you can say, like 1-bit comparator first. So suppose I want to have 1-bit comparator. So how I can make the 1-bit comparator? That is, now I just tell you about that. Now I am not having the digital numbers here. I am decimal numbers here. I am having now digital numbers. So my A and B can be of, you can say, only 1 digit. 1 digit means what it could be. When I say 1 digit means your A can be like this. Suppose I can say, if I prepare a table here. So what I can do it like this. Suppose okay. Now I'm having 2 numbers, so I'm writing that at the input side, number A and B. Now what could be the position? Your number A can be 0 or it can have value 1. Similarly, your number B can also value 0 and it could also have value 1. Means you are having 2 variables and they both having 2 different possibilities to get the value there. So according to that, how many possibility you can have at the input side? It could be like this, that your A and B both could be 0. Or you can say your A is 0 and B is 1, that is also one of the possibility. Or A is 1 and B is 0, that is another possibility. And they both are equal, 1, 1, that is another possibility. So these are the 4 different possible combinations can come on the input side when you are going to work with a single bit comparator, right? And here, how many outputs we need to have is, we need to have the outputs, that is 3. What are the 3 outputs you need to have? I need to add 2 more columns here. That is for representing 2 different other outputs. Right. So what I have here at the output side, you can say first condition that you can have is, let us say A greater than B. Right. That is one of the answer you can have at the output side. Or you can say, could have one more answer, that is what you can say A equal to B. This is what your outputs. And you can also have A less than B. So these are the 3 possible outputs you can have. So these are your outputs, all 3 which I am mentioning here, right, on this side of line. And these are your inputs. Your inputs are only 2, that is your number A and number B. Now you need to find out what is the output for each of that input combination. That is, you can say for the first condition, when your A and B both are 0, 0, you can say that your answer for A greater than B will be going to 0. Answer for A equal to B, that is going to be 1, because it is condition that true, because they both are equal, 0. And this condition also going to be 0, isn't it? Likewise, you can say for the 0, 1 condition. In 0, 1 condition, you can say your A is not greater than B, because A is 0 and B is 1, so it will come 0. Even they both are not same, so it will come 0 here also. And here you can see that your number A is less than B, that is the condition. So you can say it will be giving the logic 1 over here. Now when 1, 0 is there, you can say your A is greater than B, so it will come 1 here. and these two conditions are not exist, so it will come here 0. Likewise, for this last condition, you can say here it will be 1 because they both are equal, and these two are going to be 0. So this is how you can fill out the truth table of this single bit comparator circuit. Right now, what we are talking about 1 bit comparator. Right, your topic we are discussing, that is 1 bit comparator. So are you getting this, what I'm talking here about this 1 bit comparator?
Yes, sir.
Yes, sir.
Okay, so in this 1 bit comparator, these are the 3 outputs possible. Now our aim is to realize this using the circuits. Right, so how we'll be doing this? How can you implement the circuit here? What could be there in that black box? That is what used to have a comparison. So what logical combinational circuit you could put in that box so that will be performing this task and giving you these 3 outputs? Yes, anybody of you can just tell me about that? By looking at the truth table of this comparator circuit, can you get some idea that what could we have in that circuit? What type of logical combination we can put inside? Yes, anybody of you can get any idea about this?
Sir, for
Yeah.
A equals to B, we can use XOR gate.
Okay, but it's not look like XOR gate. It looks different than what you say. Your thinking is correct, but the gate which you are suggesting is not correct. Instead of XOR, you can just verify truth table. Is your XOR gate can give this kind of output?
It's XNOR, sir.
Yeah, it's XNOR, correct. So one thing we can do for that case, A equal to B, we can use the exclusive NOR gate there. That will be giving you that kind of output. Okay, so that thing can be there in that. So let us do that. Let me prepare a block here. Okay, suppose I just going to prepare that kind of box here. You can take this circuit as a, and I can take inputs. So let us say I can give the 2 inputs here, input A and B, and for getting one condition output, that is if they are equal or not, I can use one exclusive NOR gate. So it will be like this. And here there will be a bubble. So this is what one output you are getting. Now can you suggest me for remaining 2? If your A equal to B, then this output is going to logic 1. For other case, it will be 0. Right? That is what you can look at from the table. Now for A greater than B and A less than B, what could be the circuit we can implement inside? Yes. Anyone else now? Subham, Pujan, can you give me some input here? Hello, Subham, can you hear me? Subham, I'm audible to you or not?
Yes, sir.
Then just give me reply. I'm asking you. whatever you say about that thing, what idea you could have in your mind for that thing? Let's say for A greater than B, what could be at the output side, or what circuit you can use for that? Vartika, can you give your answer for this?
Sir, I don't know.
Kevin, do you have any answer for this?
Sir, no idea.
Okay. Nisargi, can you think on this now?
Sir, no idea.
Okay, so let's say first tell me about A greater than B condition. Okay, so you look at the table. Again, you recall the thing we discussed about min term and max term. So what are the min terms present here in the case of your A greater than B condition? If I say this will be your min term number 0, isn't it? This will be your min term number 1, then min term number 2 and 3, right? And now if I write down the output Boolean expression for this condition, that is A greater than B, so what I can write it for? I can say that A greater than B, that is what my output will be equal to, which min term is present there? Min term present here for this output is what? It is M2. Right? So I can say it is equal to M2. Now what is M2 equal to? I can say it is AB bar. Right? So this is what a simplified Boolean expression for that condition. Now AB bar means what? It is the AND operation of A and B bar. What I can do here in this circuit, I can take input A from here like this, and I can take input B and I can give one NOT gate over here so that it will make it B bar. And then I will perform an AND operation. Isn't it? So what output I will be getting here? It will be, you can say, A greater than B condition. Right? In Boolean expression, you can say it will be giving you, here it will be A B bar. Isn't it? Are you getting all of you what we are doing here?
Yes, sir.
Okay.
Yes, sir.
So now can you tell me that what can we do
Yes, sir.
for A less than B condition?
So it's not A gate first and then AND gate.
Okay. That means in that case you can just look at here that the term present for A less than B is this one, right? That is, you can say M1. So I can say for the condition A less than B, you can write down the min term present, that is equal to M1, and that M1 can be written as a bar B, like this, and that is indicating you the AND gate operation or AND logic operation between A bar and B. So what you can do here in that, you can take your B directly from here and give it to the AND gate, and we will be taking A from here and we will passing that through first NOT gate. So it will give you A bar, and then you will be performing the AND operation here, right? And that will give you output condition, that is A less than B. Right? And here what the condition you are getting here, it is A bar. So this is what your, you can say, 1-bit comparator. If your input number or digits which you are going to compare is having only 1 bit, then that two number can be compared by this comparator circuit. Can you understand this? That when you give that two bit
Yes,
as
sir.
input, you will be getting any one output of these three outputs to be logic 1, and remaining two outputs will be logic 0. Okay, so this is about 1-bit comparator. Now when you have the 2-bit comparison, this is, I said you about only 1-bit comparison. That if you have a 1-bit comparison requirement, that means your number A and B having only logic bit 1 or 0, not any other number of bits, then you can go with this circuit for that. But now suppose you have the 2-bit comparison requirement. Okay, so for that what can we do? Okay, now what we want to do is we want to make a 2-bit comparison. So for 2-bit comparison, what can we do here? For 2-bit comparator, now whatever your numbers will be there for the comparison. Let us say we have the numbers here A and B again. That is what we are going to give at the comparator input. Okay, and that comparator will be going to perform the task of comparison. So now here it is a 2-bit comparator. Can you tell me that how many output could be there in that 2-bit comparison or 2-bit comparator? Hello? When I say I want to have a 2-bit comparator, what could be the number of outputs we have in that case? Hello? Am I making my question clear to everyone?
So 3.
Okay, one answer is coming, that is 3. Anyone else?
7.
Will be 7. Okay. Is there any other answer I can have here?
Three.
Okay, Kevin is saying 3 only. Okay. What about others? All of you just.
3.
Okay. Next, anyone else? Okay. Anyway, obviously your answer is number that is number 3 only. Why? Because you can just simply understand that whether it is of a 2-bit number or 3-bit number or 5-bit number, when you are comparing, your comparison could have only 3 options. That is, either your numbers could be same or one is less than greater than to others, right? That means there are only 3 possibilities to get your output in case of comparison, right? Suppose you are comparing decimal numbers with a 2-digit, then you can say that what the answer could be. Will be the same. Either they could be same or they could be not same. If they are not same, then you can say one is less than to others or one is greater than to others, like that. So that is only the same thing you can have here. So it doesn't mean any change in the output, whether it is 2-bit comparator or 3-bit comparator. Your output will be 3 only. So here you can have again same 3 condition. That is your A equal to B, or you can say A less than B, or A greater than B. Okay, so these are the three conditions you can have. Now when I say it is a 2-bit number, that means I can say my number A will have two numbers like this. You can say it is A0 and B0. Sorry, A1 and A0 for the number A, and I can have number B1 and B0 for the number B, right? 2 digit. That means your number A can be having like that 0001, 11, or 10. Likewise, your B can also have that four possibilities. Right? It's a 2-bit number we are talking. So when you are talking about 2-bit number, your A can have any one of these two possibilities, right? What are that? Your A can be 00, it can be 01, it can be 10, or it can be 11. And same thing is applicable to your B also. That your B also can have 00, 01, 10, and 11. When I say I have this 2-bit number, so it could be any one of these four. So when you are comparing now A with B, you need to check out all that four conditions, right? So how many combinations are going to there for that? So if I just make a table of that, you can come to know that for that case we are going to have larger number of inputs possibilities that you have to compare with to get the answer, right? Because here now how many we have? So first of all, let us me just do. First of all, let me make the columns of A here input, then columns for input B, right, and then there are 3 columns for the outputs. Let us just me draw all that lines here first. Anyway, let us these are the numbers. Suppose here, if I say this is my number A, this is my number B, and here I am having the output condition. That is, you can say A greater than B, and here let us say condition A equal to B, and here let us say A less than B. Okay. Now in A, I could have the two numbers separate. That is, it is A1 and A0, right? So that I can take a separate part here. So let us me make one more line here in this. Same way for B also, it will be having two numbers, right? Now what you can hear is your A number your number A can be 0 0 first, means your A1 is 0 as well as A0 is also 0, right? Now for that 0 0 condition, you can have all the conditions for B. That means I can keep my A as like this 0 0. Right? And for that your B can be 0 1. It can be B can be 0 0 first. Then you can say it will be 0 1. It can be 1 0. It can be 1 1. All four possibility of B with the single entry of A, right? Then after, when your A is equal to 0 1, at that time also your B could be having any one of these four possibilities, right? That is your, we can say B can be 0 0 here. Your B can be 0 1. It can be 1 0. And it can be 1 1. Like this, you can do it. Then after, when your A is equal to 1 0, your A is equal to 1 0, in that also you have to check for all the condition of B. Right? That is your B can be 0 0, or it can be 0 1, or it can be 1 0, or it can be 1 1. Correct? Likewise, the last condition, that is when your A is equal to when your A is equal to 1 1, for that condition also we have to check for all the condition of B. That is, it can be 0 0, it can be 0 1, and it can be 1 0, as well as it can be 1 1. Right? So this is how you can have total 16 possibilities on the input side. That is, when your A is equal to 0 0, at that time your B can be any one of these four possibilities of B. Likewise, for all four possibility of A, you have to four possibilities check with the B, and that's why 4 into 4 you can have to total 16 possibilities, right? Now for all these 16 possibilities, you need to find out your output condition. So let us say first for the condition here, when your A equal to 0 0 and B is also 0 0, so you can say in that case your output condition will be A equal to B, and this both are going to be 0, right? Likewise, for this second condition 0 0, then your B is 0 1. So which one is larger? B is greater than, right? So you can say this condition is going to be 0. Your A is not larger than B. A is not equal to B also, but A is less than B. That is true. So likewise, we have to fill out all these conditions in whole table. So this 0 0 and 1 0. So you can say this will be 0 condition there. This will be also 0, right? And this will be logic 1, because here again B is greater than. Same with for this condition 0 0 and 1, right? Then after, when your A is 0 1 and B is 0 0, you can say this will be greater than. So this is 0 and this is, you can say 0 at that time. Then after 0 1 0 1, so both are equal, so you can say this is 0, this is 1, and here is 0. Then 0 1 1 0, so you can say number A is less than number B, so you can say this will be 0, this will be also 0, and this is going to be 1. 0 1 1 1, so your B is greater than, so again here it is 0, here also 0, and here it is going to be 1. Then 1 0 and 0 0, so this is going to be 1, this is 0, and this is also 0. Then 1 0 0 1, again this is going to be 1, this is 0, and this is 0. Then 1 0 1 0, so both are equal, so this is 0, this is 1, and this is 0. Right? Then 1 0 1 1, so you can say this is 0, this is 0, and this is going to be 1, right? Then 1 1 0 0. So you can say this is going to be 1, this is 0, and this is 0. 1 1 0 1. So this is going to be 1, this will be 0, and this is also 0. Then 1 1 1 0. Again, this is 1, this is 0, and this is also 0. And for 1 1, it will be like this. So am I making this thing clear to everyone? That how we are going to check out all the conditions for this 2-bit comparison? Hello?
Yes, sir.
Well, are you getting what I'm doing here?
Yes, sir.
Right? I'm looking at all the possibilities of your 2-bit number
Yes,
that
sir.
could be coming at the input side of your 2-bit comparator. And for all that possibility which can be there at the input side, you need to decide that what could be output at that time in that comparator, or you can say 2-bit comparator. Is that okay to everyone?
Yes, sir. Yes, sir.
Yes, sir.
Okay, that's fine. Now we need to find out the circuitry. Like in the previous case, here we have seen that how can we implement the logic circuit for the comparison of 1-bit comparing number A and B, right? Same way here also you have to find out the logical circuit that you can use for comparing that to numbers. So how will be finding out that? Here you have these 3 outputs, right? And that for that 3 outputs you may note down like that. Suppose I'm taking let's say this condition A greater than B. Let me call it is function f1. For this condition I can say function f2, and for this condition I can say function f3, right? So how can we write down the function f1 first? Suppose I want to write down the function f1. Now what are the inputs here for the functions? Here you can see your inputs are a1 a0 b1 b0. There are 4 inputs. So I can say it is a 4 variables function. Your inputs are a1 a0 b1 b0, right? And for this 4 input function, what are the minterm present? Can we write down the minterm present here for this function f1? Can you just give me the numbers minterm present here? Hello? By looking at this table, can you just list me the minterm present for the function f1 here? Hello? Hello, why you all are so silent? It's now we are moving towards the KMF. Right? We are going to first find out the function, and then we will be minimizing that using KMF, and we can come to know what the minimized function, and that could be implemented in the circuit. Hello. This is a very simple question I'm asking. Why you are looking all silent? I'm asking you just about the thing which are the minterms present in this function f1. F1 means the A greater than B condition. That is what the output you have here. So which are the minterms present in this? Can you list out the total number of minterms present here? What are the total number of minterms? Hello?
6.
Total minterm is 6. Kevin is giving that answer. Anyone else?
6.
Emily is also saying 6 number of midterms are there total. Are you saying me 6 number of midterms present, or you can say total? Hello?
Yes.
Are you saying about the present midterm in that function or total midterms in this system?
Present midterm.
Okay, present midterms. Yeah, that's correct. So can you just tell me that numbers which that 6 midterms are there in that function?
Yes, sir.
Yeah, please.
M4, M8, M9, M12,
M
M13, M15.
13 and 15. See, the first midterm which you are having here, you should start numbering from 0, isn't it? Your first midterm which is present here, that is what your midterm number 0. So you have to say this is your midterm number 0. Then 1, 2, and you go in increasing order, and your last is going to be 15. Isn't it? So which are the midterms here present now? You can see here, this is 0, 1, 2, 3, then 4. So 4 is there. Then after 5, 6, 7 is not there. Then after 8 and 9 is there. So you can write down that. So I can say 4, after that it is 8, then 9. Okay. After 8, 9, 10, 11 is not there. 12, 13, 14 are there. So you can note down that numbers. So after 9, it is 12, then 13 and 14. So these are the midterms present in your function f1. When I say f1 means it is the condition a greater than b. That is what our one of the output, right? So how can you implement the kmap for this function now? To find out the list number of member present in the output side. Can you just prepare a kmap like this now, everyone, to find out the minimal function of this, so that we can have the circuitry for this first output or first comparison result. So here you have to write down your present condition, or it is a variable. So let us say I am putting here a1, a0 as here. Let us say a1, a0, and here I can say it is b1, b0, because these are the variables we have, right? Now minterms number you note down here, it will be 0, then here it will be 1, then 3, then 2. So in sequence you can note down it, right? Here the first condition will be your 0, 0, right? Then 0, 1, then 1, 1, and last will be 1, 0 for the input b1 and b0. Likewise here will be 0, 0, 0, 1, 1, 1, and 1, 0, right? So minterms are there here like this: 4, 5, 6, 7, 6. Then here it will be 8, then 9, 11, and 10. Right? Then 12, 13, 15, and last one will be here 14. Okay. Now here you have to enter the present number of minterms. So which are the minterms present here? 4, 8, 9. So I can enter here 4 is 1. Then 8, 9. So it will be 1, 1 here. 4, 8, 9. Then 12, 13, 14. 12, 13, and 14. Right? These are the minterms present here you have. Now what you have to do is you have to form the group to get your answer. So how will you form the groups? Here we can have one group here that is of these 4 members, right? And one group that you can have here that is for these two members, and one you can make by having the group of this element and this one, isn't it? So these are the 3 groups you can have, and according to these 3 groups you can just find that what could be the minimal function of this tree. Can you just write down for this 3 group and what is the minimal function output for this? So what I can write down here, f equal to minimal function here at the end f equal to. I can say f is equal to, or I should say f1 is equal to, for this 4-member group, what is the answer? Here a1 is going to remain constant, right? And here on this side your b1 is going to remain constant. So I can say it is a1 b1 bar, a1 b1 bar, then plus the group of this number. This is what, let's say, second group. So for that you can see your variable a0 is remain common and b1 b0 is there common. So I can say it is a0 into b1 bar then b0 bar, right? Plus this 2-member group. Let us say this is the group number 3. I'm saying this one as the group number 3. So for that your element b1 not b0 is common, 0 0, and a1 a0 is there. So you can note down like this, a1 a0, right? And then last one is b0 bar. So can you get it, this what I'm saying here about this now? Hello?
Yes, sir.
Yes, sir.
So now what you have to do is you have to implement this function f1. That is, when you are going to compare your 2-bit numbers, what can we do now? Let us take one part here. I need to draw that circuit here, so you will get it idea here clear. Okay, anyway, now let me just draw that circuit here inside the box, so that will make you understand about that part. So suppose I am having this as a function. Okay. Now in this, we will be having 4 input lines. What are that 4 input lines? That is, you can say your input A1, though your number A is there, we are comparing only number A and B, but your number A will have this 2 part, that is A1 A0, and similarly your number B will have 2 lines, that is B1 and B0, because it's a parallel bit comparator, you can say, right? So this is what your number B is. You are comparing your number A and B having 2 bits. So first of all, according to this reduced function, what you are having your function f is your function f1. That f1 is nothing but it is the condition of A greater than B, right? So for that condition of output, first of all, what you have to do is you have to do this thing, that is your A1 B1 bar. So what I can do, from this A1, I will be taking one line, and from this B1 also I will be taking one line. Later, before that, I need to extend that line of all that numbers. So this is the line of your A1 and A0, then this B1 and this is B0. Okay, so first of all, I'm doing this A1 and B1 dash. So we'll be taking from B1 here like this, and that B1 will be passed through the NOT gate. So it will be giving you B1 bar, and that will be given to one AND gate. So that will be first output, that is your A1 B1 bar. Right? Here you will getting A1 and B1 bar. Okay. Second, what you required is A0 B1 bar B0 bar. So first of all, you have to take A0 from here. So you take your A0. You will take one more AND gate here. Second input, that is A1. So you can take A1 directly from here also. Right, and the third input is B0 bar. So for B0 bar, we have to take it from here. And that will be first passed through the NOT gate, and then it will be applied to here, right? So this AND gate will give you A0 B1 bar and B0 bar. Sorry, A0 B1 bar is there, so I think I done wrong thing here. This is not there, A1 is not there. The second input going to be here. Let us redraw this part. Here that first B0 bar will be drawn through NOT gate here like this, and it will be given. And your B1 bar, that is already here, so I can take it from here B1 bar directly, and I can give it like this. Okay, so that is what the second part. Now third one is A1, A0 and B0 bar. So that now I can have one more AND gate here. Now A1, that I can take from here. Then after A0, so A0 is coming here, so I will be taking it from here. So this will be A0, and next one is B0 bar. So B0 bar we can take from here, or otherwise you can directly put one NOT gate here directly and you give it to this, like this. Okay, so here you are getting the third term, that is A1, A0 and B0 bar. Right, now these three outputs you have to give one 3 input OR gate. So that will be making summation of all these three terms like this, and that is what your function output F1, that is equal to condition is A greater than B. So can you understand this, everyone? Hello?
Yes, sir.
Okay.
Yes, sir.
Now can you just do the similar task for condition F3, that is A less than B? All of you just prepare the function F3 from this table. You can write down it like this, whatever minterm present. Then you can minimize using kmap, and whatever function you are getting, that you have to implement like this. Can you do it? Hello?
Yes, sir.
Okay, just do it that. All of you just do this. I'm keeping table visa here, so you can just get easily from that. Okay, here is the table. Yes, anybody have done it? Hello. Now, is there anyone got it done?
So F3 का आंसर मिल गया.
What you are saying, Emily?
अब A1 bar B1 plus A0 bar B1 B0 plus A1 bar A0 bar B0.
Okay, that's the reduced function you are saying, right?
Yes.
Yeah, it's correct. Okay, so that now you can implement in the same order as we have done for the first case. Okay, can you all see the circuit I'm showing you right now?
Yes, sir.
See, this is the circuit showing you the all three condition output. See, the first one, that's what we already have implemented here. You can see that right now we are first here we have done that is for A greater than B, right? And now here you look at in this circuit. Here this is the condition first here done, that is for the A less than B. This one condition is for A less than B. That is, you can see here. Here it is A1, A0 coming. So this will be going to be your A1 bar, and this is going to be your A0 bar. Okay, and this B1, B0 are coming. So this is what your B1, and this is the line for B0. Now that is got connected here in this NAND gates. Okay, so here it is, instead of AND gate they have used NAND gate, because here they have used the NAND gate again. Right? If you are using AND gate over here, let's say this is 1, 2, 3. If you are using this 3 gate as an AND gate, then this number 4 should be OR gate, right? And if you are using this NAND gate, then all 4 could be a NAND gate. That's why it is. So this is what the same order you have done. Right here you can see that what you are getting right now for your function f3, that is first you will be getting b1 and b0, right? Is it b1 b0 or anything else? Hello? Here in your function I think your f3 could be like this. Function f3 that is b1 a1 bar plus, you can say it is b0 then a1 bar a0 bar plus you will be getting b1 b0 a0 bar. Is this what your answer? Hello? Are you getting all of you this reduced function f3 after using your KMAP?
Yes, sir.
Yes, sir.
So that function is implemented here, and so that will giving you a condition your a less than b. That is what your f3 here. Okay, can you understand that or not?
Yes, sir.
Now second thing what here it is done is you can see that here two exclusive OR gates are used. Let us call this is, let's say, x1 and x2. So this x1 x2 is what? It is your two exclusive OR gate, and they are comparing your b1 a1 bits. So you can see here this x1 is taking two inputs, that is b1 and a1, and this will give you output of comparison that two bits only. Right? Earlier you can see here in this case we have used to have this kind of exclusive NOR gate, right? What it is doing, it is giving you output condition whether your a equal to b or not. Same thing is we have done here. That is what your x1 and x2 is doing. That is, your x1 will say you whether your b1 or a1 is same or not, and x2 will tell you b0 and a0 are same or not, right? And that is given to this AND gate. So this AND gate will be doing what? If this both conditions are true, that means your a1 b1 are also same and a0 b0 also same, then you can say that your output of a is same. That is what condition your a equal to b, right? So this is what the condition you will be getting here. That is your function f2. Are you getting? So for middle function, that is comparative analysis, if your A equal to B, can easily be done with the help of 3 logic gates only. You can use 2 exclusive NOR gate, that is X1, X2, and 1 AND gate, that is A, as I shown here in this circuit you can see. So X1 will compare your A1 and B1. If your A1 and B1 both are same, then only that X1 output will be logic 1. And if your A0, B0 are same, then only your output of X2 will be logic 1. And if that X1 and X2 both are giving the logic 1 output, then only your output of logic AND gate A will be 1. Otherwise, it will be 0. Can you get it, everyone? Hello.
Yes, sir.
Still only one is reply coming here. What about others?
Yes, sir.
Just
Yes, sir.
is there any difficulty? Then
Yes,
just let me know. Okay.
No, sir,
and-
no doubt. Clear.
Okay.
Clear,
Now-
sir.
Okay. Now you look at here in this circuit. In this circuit, the third part, that is your function f1, that is A greater than B, is generated here, and that is only by using one exclusive, sorry, not exclusive, only NOR gate. You can see here. This is what I can say. Let me say a NOR gate. So I can just put NR over here. So this NOR gate will do what? It will be taking one output from this A equal to B, that is your F2, and one input from this, that is A less than B. And what is the function of NOR gate? That your NOR gate will give you output logic 1 when there is both input are logic 0. That means if the condition A equal to B is not exist, if condition A less than B is also not exist, then what condition remains there? That is A greater than B only, isn't it? That means if your these two conditions, A equal to B and A less than B, are 0, then this NOR gate will give you output condition that is A greater than B. Is that clear to everyone?
Yes, sir.
Yes, sir.
Okay. So this is how.
Yes, sir.
Okay, thanks. So this is how we can have the 2-bit comparison. You just think of the circuit if you are talking about comparison of, let's say, 32-bit comparison. Here we have just compared the 2-bit number. Then also these are the number of logic gates you have to connect in this manner. That is for comparing only 2-bit number, that is A1, A0, B1, B0. When I say 32-bit comparator, it means there will be 32 bits of A, that is A 31, 32, 30, 30, 29, 28 up to 0. Then after B 33, 32, 31, 30, then 29, like that. So there will be a lot of complex circuit, right? Lot of number of logic gates are there included in that, which is not possible to done manually connections. That is going to become come in the logic IC pack only, right? But right now we are just able to understand that how this logic combinational circuit can be realized to make the comparison of digital numbers. So I hope this is clear to everyone. Is that thing clear to everyone now?
Yes, sir.
Okay, and so this is what the theoretical aspect which we can discuss today. Actually, that virtual lab which we are using for our virtual simulation to verify this condition in a virtual manner. That lab today is not getting open due to some site issue there on the virtual lab site. Okay, so we'll be performing this virtual simulation in our next coming lab. So today we are just keeping up to this. If you have any doubt in this theoretical discussion we have done for this comparator, then you can ask me. Otherwise, you can give your attendance and then we can leave. Okay, thank you all. I think you all have given your attendance. If anyone has not given, please just do it. I'm going to end the session very soon. If you have any query, just let me know. Thank you all.